Okay, so I'm James Jones. I work on Linux graphics drivers at NVIDIA. And today I'm going to give an update on the generic Unix device memory allocator mechanisms, specifically on some work I did to implement a prototype of the mechanisms in the Nouveau drivers. So if you don't know what I'm talking about, don't worry, I'm going to give an overview of what the allocator is and how it was described 2 years ago at my talk in XDC 2017 and the brainstorm we did at XDC 2016. And then I'll talk about what's changed in my thinking in this prototype versus the last prototype. I'll talk about the implementation of the concepts in Nouveau and the open source driver stack in general and how that went and how it maps to the existing APIs. And finally, I'll talk about the results of that implementation work and give some next steps. To start out with the review. The allocator itself, or the project anyway, came out of some conversations we had, I think on one of the Wayland mailing lists after NVIDIA proposed the EGL stream patches to the Weston project. So there was a lot of debate over those. I'm sure everyone remembers that. And in the end, there was kind of just no agreement. You know, the patches weren't merged upstream, but we're kind of at a standoff over, you know, were the benefits of AEGL streams provided versus GBM actually beneficial and were they worth pursuing, or was it something we should just ignore and use the upstream methodologies and go from there? So at XDC 2016, we had a big workshop and talked about, you know, if we wanted to have the world's perfect mechanism to allocate device memory on Unix, what would it look like? What would the goals be? And what would the design look like? So the list of high-level goals here are kind of a brief summary of what we came out of that talk with. We wanted to be able to arbitrate the allocation properties across multiple devices and multiple device engines. So basically giving the needs of a bunch of different devices or a bunch of different use cases for a 2D surface. We wanted to be able to combine all of the requirements of the different pieces of hardware that we'll be talking to into one big set of themes, and then choose the optimal ones out of that set somehow. There was a lot of support for having something that would work for things besides graphics APIs. So you wanted to be able to support, you know, not just 3D, but also things like cameras streaming input to the system, video encode and decode drivers, or really anything that works with a 2D surface and wants to interop with something else that works with a different kind of 2D surface. I really wanted to support vendor-specific capabilities, including fully opaque capabilities, and this was not so much that we didn't want to hide what the capabilities were or what the hardware could do, but we wanted to be able to ship new hardware into an existing software system without actually updating all of the software. We just wanted to be able to plug in a driver that would expose the new capabilities of the new hardware, and that have that somehow just magically work with the old software stack based on the kind of framework that was already in place. And finally, another thing that was really important from the NVIDIA point of view was to be able to support transitions. And by transitions, I mean having a system that's more or less in one steady state, and then moving it into another steady state without reallocating the buffers, and still have, ideally, completely optimal properties of those buffers. So transition means transitioning from one use case to another use case, and in doing so, probably modifying some of the buffer layout properties in the process. So with those set of goals in mind, I came up with a prototype implementation that I presented at XDC 2017. From that slide deck, I had that prototype implementation was a standalone library. And so this is the idea I had of where it would fit into the existing graphics ecosystem on Linux. So you can see that the allocator library or API is being used by Wayland compositors, Wayland, or in general any application. It would especially be used by things like what we saw yesterday, like the Vulkan WSI layer implementation, or the equivalent thing in an EGL or Vulkan driver that would allocate the surfaces that an OpenGL or graphics application, like a Vulkan application, would use to present its results to a windowing system. That was one of the primary use cases. And it's also kind of a special case use case because that's something that could potentially already be in a driver and have sort of custom code per vendor. But the idea was that that's obviously not the way we want things to go in the future. We want that to be in a layer like is being proposed. So the interfaces that that layer uses have to be standardized as well. So then on the back end of the allocator, the idea was that it would have plugins that could be loaded into it. So you could have multiple different vendors ship their plugins, and not even necessarily vendors, but it could be multiple different like kernel subsystems or other backend libraries. So you could have like the Ion driver provide an allocation for any device in the system, or you could have vendor-specific drivers providing special types of allocation that they need for their hardware that only they know about. So that's where it fit in. For the Allocator API, from the brainstorming discussion, we came up with this list of objects that we built the API around. So it starts off with assertions. An assertion is basically just the most basic information you can provide to describe a 2D surface. So it's the width and the height and the format. So pretty much anytime you allocate a 2D surface in any API, you're going to have these things available. And they're not really negotiable. If you ask for a surface of a given width and you don't want the allocator to come back and say, like, no, I can't do that width, I can do a different width. That's not going to work. So these have to be things that are set in stone by the application. And there could be more, but these are the important ones that came up with to start out with. Related to assertions, the other input to the allocator request would be usage. So usage is more complex types of input data. This would be things like, I want to use my surface for 3D rendering. I want to use my surface for texturing or sampling, those types of things. Or I want to put it on some kind of display hardware. I want to have it be a destination buffer for a camera. All those are usage data that you would specify through this. And usage would be specific to a particular device. So you might say, I want to use this thing for 3D rendering on this NVIDIA GPU, and I want to use it for texturing on an Intel GPU. So then those would be what you would pass into the allocator. The allocator would feed you back two different types of objects. There would be constraints and capabilities. So constraints describe a limitation of the surface you're trying to create. So you might have some device say, okay, I can create a surface that you can render to, but the pitch for that surface has to be a multiple of 1024 for whatever reason. That's just one example. And the idea is that the constraints would be baked into the allocator library itself. So not the actual values of the constraints, but the constraint, the types of constraints. So you might have one constraint type that is pitch alignment, like I was talking about. You might have the initial allocation base address alignment would be another kind of constraint. You might have a maximum pitch that your hardware could support, those types of things. So then capabilities are sort of the logical opposite of constraints. They are, whereas constraints limit an allocation, capabilities are things that enable an allocation. So the most obvious example of a capability would be like a tiling format that your device supports rendering or texturing from if you're a 3D device. You might have capabilities like device local memory that you can make use of on your device. So you could say, you're going to do rendering. Oh, I can do that. If you're going to render on my device, you should probably place your memory in, or place your surface in memory that's local to the actual GPU. So those could be expressed that way. And capabilities were designed such that they could be opaque to the allocator library. So you could have each allocator backend could define its own types of capabilities that the allocator didn't have to be aware of or be able to introspect, but it could still combine them into what we called capability sets. And capability sets are what you'd actually return to the application. And the capability set is a compatible set of constraints and capabilities. So you take a bunch of these things and put them together in a set. And the backend driver that defined that set will confirm that that set, if treated as is, will be compatible with that hardware for that particular usage case. And then the idea is you could take these capability sets, and they would be serializable. You could transfer them across process boundaries and everything. And so you could have different parts of the system querying their different usage and getting back capability sets. You could pass all the capability sets around, and you could end up merging them using some defined Boolean kind of logic into a smaller set of capability sets that would work for all those different usages. Or sometimes the result of that logic would be nothing. You would get no capability sets out of that, and then you would know that those particular sets of usages were not compatible, and you would have to introduce, say, a copy or a blit somewhere in the system to make your particular use case work properly. So those were the parts of the API that I actually prototyped and demonstrated in 2017. And then the next steps for that presentation, I listed out usage transitions as something that I wanted to work on. So the idea behind usage transitions is that, it's based on the Vulkan idea of like layout transitions, where you have some Vulkan image and you're using it for rendering. If you want to start using it for, say, a transfer operation, you have to transition it over to the optimal transfer format for that particular hardware. And in Vulkan, there's not really any. It doesn't tell you if the transition is actually doing anything or if it's actually providing you some kind of measurable benefit. It's up to you to kind of determine that on your own. But I wanted to make it much more explicit when you needed a transition and when you didn't. And with the allocator mechanisms from the last slide that we described, I thought it would be possible to generalize these across devices and make them more, broadly usable. So you could have, say, if you had some GPU and a separate set of like display hardware IP, and they both used a compatible set of tiling formats, but they had some slightly different quirks in how they had their caches working or something like that. The allocator should have been smart enough, or should have been able to have a backend developed for it that would be smart enough to say, okay, you can use your optimal tiling format for these two pieces of hardware, but when you go from one to the other, you're going to have to do some kind of transition that prepares it for use on the other one, and maybe transition it back afterwards to be used for the first use case again. These would be more complex than the transitions represented in Vulkan, potentially. So the idea was that the applications wouldn't be able to name them explicitly. There might be too many of them, or they might depend on the system at runtime. So the idea was the applications would just say, I want to use these two usages. Is there some metadata that describes the transition between them? Then the allocator library would tell you back, yes, there is, and here it is, or no, there is not, and you can't do that, in which case, again, you have to do a copy. And then the application would then take that metadata and pass it into, I think we agreed that it was only the 3D APIs that would be able to do the actual transitions, since they're usually the ones that have the capability to do that. And then those APIs would expose some extension that would allow you to actually perform the transition given that metadata. Okay, so that's a review of what happened already. I'll stop here real fast. Are there any questions on that so far? Everyone's watched my talks from 2 years ago? Cool. Good homework, guys. Okay, so what's changed since then? So after that talk, I got some feedback. There's some good feedback from the audience, and then afterwards in the hallway track, of course, there always is. So I think Daniel Stone said, this sounds pretty good, capability sets look nice, but where do format modifiers fit into that, since they're already here and do some of this stuff? And at the time, I think my response was something like, format modifiers are mutually exclusive with capability sets. They perform kind of the same thing, but capability sets are like format modifiers 2.0. And my concern was that format modifiers were too limited and didn't have enough space in them to represent all of the data that I would need for our crazy NVIDIA hardware and stuff. Separately, I think I talked to Chad Versace in the hallway later on. He was currently working at the same time on integrating DRM format modifiers with the Vulkan API, trying to figure out what that would look like. And he really, really wanted to make sure that that would work on NVIDIA hardware somehow, even if not now, maybe in the distant future when I came around to his way of thinking. So he was really patient and spent a lot of time talking me through how the API worked, and he addressed a lot of my concerns about the API itself, even though I was still concerned we would have about 1 million format modifiers. He was like, that could potentially work if it's like slightly less than 1 million. This is how everything works, and here's how the plumbing goes through. And I think we did resolve a couple things at the in the Vulkan API level that would make format modifiers work a little bit better in Vulkan than maybe other APIs. But overall, he was just really good at explaining exactly how the whole system was meant to work. And somewhat related to that, I think it was KRH that said, this sounds okay, but why are we having this whole new API to describe usage when there's already a bunch of APIs that describe usage? Like, Vulkan has a whole bunch of flags that describe exactly how you're going to use a 2D buffer. OpenGL kind of implies the same thing by saying, I'm going to do all these things that OpenGL can do with the buffer. So why not just ask them what their capabilities are rather than having a new API for that has to redefine all this usage stuff. And we'd considered that idea when we were first developing the high-level ideas. But at the time, I didn't really want to go that direction because I was worried about some clients of the allocator, specifically Google has said they were interested in possibly layering Graalvk on top of the allocator library. I didn't want to have this circular dependency where Graalvk depends on OpenGL and Vulkan to query its capability sets and everything. But then again, EGL and Vulkan themselves would depend on Graalvik for their allocation in some cases to get this kind of circular thing. And I was really worried about that. And I also thought you could define much more fine-grained usage if you had like a standalone library that could have vendor-specific, really complex usage cases defined. So I had some concerns there, but it was an interesting idea to think about for sure. And then when we started talking on the mailing list, I think after the 2018 talk, or 2017 talk, there was this debate, I think I might have posed the question actually, should the allocator be the standalone library that I've done in the prototype, or should it just be an API, an extension of the existing GBM API and something that you build out of the existing GBM library? And there wasn't any clear direction there. I think Rob Clark said, let's build a whole new API, GBM's too tied to graphics. I think there are other people saying, no, GBM's a great place to start. And I personally kind of felt that GBM was a good place to start because it's already established in the ecosystem. And I was pretty wary of introducing another new API after having the whole EGL streams thing go through. But I don't know, it didn't seem to be a clear direction there, so I wasn't really totally sure which way to proceed yet. So we had those conversations, and I think also after 2017, I immediately went on paternity leave, so I was out away from the whole thing for 3 months. Miguel Vico-Moya from NVIDIA stepped in and did a lot of work trying to establish what the usage transition API would look like in practice, and there was some really good feedback there on how to define that and how to set up the math to deduce a given transition from a given set of usages. But after a while, things kind of stalled out, and I think people started asking me, hey, every couple months I get a message saying, hey, is that allocator thing you talked about still going to happen? Are you still working on that? Sounds really cool. But then, I didn't work on it for a couple of years. I had other things to work on. I didn't have time to get back to it. But then in 2017, or in June of this year, I think I just finished up working on my implementations for timeline semaphore in our Vulkan driver. And I think my boss saw that XDC submissions were open again and said, hey, James, could you do something on the allocator for XDC this year? And I was like, I don't know, it's pretty soon. I only have a couple weeks to put a proposal together. So I started thinking about what's the minimal thing I could do that would still, move things forward. I didn't want to repeat the same experiments or give the same talk again. So I thought, what am I really trying to do here? So the thing that I hadn't got to in 2017 was that I really wanted to demonstrate the usefulness of transitions. At the same time, I still couldn't help wondering if, I'd already demonstrated what it would look like as a prototype to have a standalone library that implemented the allocator stuff. But I wanted to evaluate the other direction as well and give it the same kind of, chance that had, and see what it would look like to develop this API on top of GBM and the existing driver ecosystem. So I started out with the same high-level set of goals, but tried to reevaluate them with this new prototype direction in mind. So we still had to be able to arbitrate allocation properties, but I thought, well, for now, let's not try to solve the whole thing. I don't have much time, so let's support only the intersection of capabilities, not the union of constraints. Constraints are still important, but I just wanted to kind of cut the problem space in half. Makes the math a lot simpler. I still wanted to support a broad set of engines and not make it specific to any particular 3D graphics API. But I thought if we don't make a whole new API and just let the APIs define the capability sets as we talked about, or as Christian had suggested to me, maybe that's still possible. If you want to use 3D APIs, you still have to query them for the capabilities, but it's still not dependent on those APIs. You can still have a whole other set of APIs that doesn't even involve graphics ones that could have these same kind of interfaces to them and report the capabilities back. I definitely still wanted to support vendor-specific capabilities because you don't want to have every single device know about every other device's capabilities. But I decided to ignore the idea of having these fully opaque capabilities where they're completely undefined and unknown to the whole driver stack. It turns out that even if you have something like format modifiers, the applications using that don't actually have to be that aware of the format modifiers themselves. All they have to do is be able to know how to query them from the driver, and then they can treat them as opaque more or less, and I think a good application does. And that's something that Chad really helped me work through when he was talking about his APIs. And then, so I still wanted to support usage transitions. I still think this is an important use case. I think allocation is, it's expensive, and it's also very disruptive to applications, as people have told me over and over again for their swap chains. So that they don't want to have to go and recreate things and lose all their content just because something changed a little bit in the Windows system configuration. and I think it's still very important. I think everyone's goal is to make sure that the steady state, when you get your application just rendering onto the screen, especially some 3D application, you want that to be running as fast as possible. It shouldn't be not making use of all of your GPU's capabilities. It shouldn't be wasting power. It shouldn't be leaving any performance on the floor. So that's still an important goal of mine. So with that in mind, here's the allocator objects overview slide again, but with some of the things that aren't included in this prototype grayed out. So we still have assertions. We still have very specific usage definitions based on other APIs, and we still have capabilities. And so what do those map to in the new prototype? Probably not too surprising. An assertion, obviously, is already in every API. So Vulkan, OpenGL, and GBM image creation parameters already include width, height, and format. Usage is defined by other APIs now. So if you want to create a Vulkan image, it already has a very rich set of usage to describe what kind of things you're going to use that image for. Sometimes usage is implied by the API itself. So if you query from DRM KMS, what capabilities do you have? They can probably assume that you're going to want to use that image to display on screen via DRM KMS. And same with OpenGL. It's just basically the same thing as Vulkan, but with OpenGL, you have to assume the image is going to be used for anything OpenGL can do. So it's basically set all of your Vulkan usage flags and just allocate an image. The capability list, is easy to break down to a single DRM format modifier, assuming that you think format modifiers work. So, if you look at these three right here, there's nothing new here. This all exists right now in the ecosystem. This is exactly what DRM format modifiers are and how they're used in Wayland today. The only really novel thing that I added was the usage transitions. And this is pretty simple once you break it down like this. A usage transition is just switching from one format modifier to another on the fly without reallocating. And so I added a new extension that could do that. So with that in mind, let's walk through the implementation stuff. But before getting into the details, the first part of this was obviously that I had to have a DRM format modifier that I was satisfied could represent all of the data that I had planned putting into a capability set for NVIDIA using the previous allocator prototype. So let me start with a little background on why I thought block linear was so complicated. It's not a super novel thing. I imagine block linear is roughly similar to tiling formats that a lot of other 3D graphics vendors have. The idea is just to arrange your bits in memory such that when you're doing 3D rendering, or when you're doing, or if you're doing texturing from a surface in a 3D engine, the access patterns are optimal for your memory banks and everything. So this format has been in NVIDIA hardware since the Tesla class of hardware in some form or another. And it consists of what we call gobs, or groups of bytes. So you take those groups of bytes. These are kind of fixed size things. And I guess this is what you would call, some people might call this the tile, but for us it's just the gob, and gobs make up tiles. These are fixed size, but the size and the layout of the bits within the gob varies per hardware, I think pretty drastically. So I think between the Tesla and the Fermi class of hardware, these became twice as high as they were before. And even between just things like between a desktop GPU and Tegra GPU, there's some very low level stuff where I think at the bit level, the bits are swizzled slightly differently, or maybe it's just the bytes, I forget exactly which it is. So there's a bunch of different versions of this itself. But if you take the gob as like a building block, then block linear becomes relatively consistent on top of that. You can take some number of gobs and combine those into one block, which I think is what you would really call your tile. And blocks can vary in dimensions. And in the general case, they can vary by width, height, and depth. So they can have some number of gobs wide, some number of gobs high. And if you have a 3D texture, they can be some number of gobs deep as well. The only limitation there is that the block height, the block width, height, and depth must be a power of 2. And that lets us represent them as their logarithmic equivalent. And as I said, the layout of the bytes and bits within the gob is very implementation dependent. Besides varying between the different GPUs, it kind of depends what format you're using to render to that particular tile with also. So we have this thing called the page kind, and the page kind can be determined from a combination of the GPU, the multi-sampling method, and the format that you're rendering to. And based on that, you can derive a page kind that the hardware will use to render to that format. And the page kind, in turn, decides where the bits are exactly in your surface or inside your gob. So if you determined all of that, you have it all these parameters set up, then you can build your surface out of an arbitrary number of these blocks. And so right there, I have an example of a surface that is 64 pixels wide and 32 pixels high. And so that's made up of a grid of 4 by 2 of these 64 by 16 byte blocks. And some of the details here are hand waved, and I think the pixels or bits in the top gob there don't actually line up to the appropriate size, but you get the general idea. So then taking that format, and that's just one of the things we have to describe in our format modifiers. So at first I was concerned that these blocks could be infinitely big. We could support all different kinds of dimensions of them, and you had to support 2D array images and 3D images and all these complicated things, and multi-sample and all this other stuff. But then Chad really talked to me. He's like, no, format modifiers don't do any of that right now. Format modifiers are used to describe 2D single sample images that are shared between mostly Windows system stuff. So while it might be nice one day to have format modifiers that can describe multi-sample images and share those directly between Wayland clients and Wayland, that's not what they do right now, so I don't have to worry about that case. And so I started looking at, and this really happened, I think, actually 1.5 years ago when I first got back to work and started looking at this again. I started looking at what I actually need to include in this format modifier to fully define a surface layout across any of the NVIDIA GPUs that are out there, and without having any ambiguities and without be able to guarantee that if you had this given format modifier, the surface would be compatible with any other device that supported that format modifier within the NVIDIA family. So that took some work. I had to do a lot of research, asking the architecture people what values could go in what fields and how many values we actually needed to describe for the particular use cases we were talking about. And I had to chase down the right documentation. But in the end, I came up with this format right here. It's a parameterized format modifier. It's a superset of the DRM format mod NVIDIA 16bx2 block parameterized format modifier that we have in DRM 4cc right now. And it should be fully backwards compatible with that. There's some caveats there that I'll go over in a subsequent slide. But it strictly defines a superset of the functionality that the old one did. And it describes some fields more precisely, well, kind of grandfathering in what I think the original ones were trying to define. So yeah, like I mentioned, in case there's more complex use cases in the future, I did leave some reserved fields in there. But there are a lot of ways to simplify things from the generality of the previous slide. So for example, you can only actually have block widths of 1 in purpose in the hardware. Some of our earlier hardware actually supported setting like 2D block sizes, but architecture determined that the blocks wider than 1 just weren't that useful, and so you can't actually get them out of our 3D engine, I don't think, and use them anywhere else, except for if you decode them on the CPU, so they're not terribly useful in practice. You don't obviously need to set the depth to more than 1 if you're not doing 3D images, so we can remove that field as well, and that takes out a lot of variability. The page kind field here is 8 bits, just like it is in our page tables, because that's where we get it from. But in practice, there's only 2 page kinds that are interesting right now for 2D surfaces with color formats, so we can simplify that quite a bit as well. We don't have to actually have the full 8-bit space of them. We just have to have 2 or 3. And then the bits besides page kind and block height here are really kind of these very specific things to differentiate different kinds of GPUs and different kinds of use cases. So you have to define the GPU generation, which defines whether or not you're using some particular kind of block linear, since it has varied over time. You have to specify the sector layout, which differentiates between Tegra GPUs and desktop GPUs, and actually newer Tegra GPUs use the desktop layout too. And then finally, at the very end, we have compression, which indicates whether or not you're going to use our on-chip, on-the-fly compression. And I'll talk about that some more later as well. Ultimately, what this comes out to is for any given NVIDIA GPU, we have to expose probably at the most 24 or 32 modifiers, so something totally reasonable. We do have to kind of construct them on a very granular basis, like per GPU, or per GPU family at least. So we track a lot more of them in the kernel and in the drivers than I would probably want to, but it is possible to make it a very finite list for applications to deal with. So that was probably the hardest part of the work, was just defining that format modifier, and getting it reviewed and making sure it would probably work everywhere. So with that in hand, I went on to look at the Nouveau driver and evaluate how that was doing with format modifiers. And I found that the support was pretty limited right now, so I wired up the format modifiers for some more use cases. As far as I can tell, and please someone correct me here if I got it wrong, the existing format modifier support in Nouveau was only good enough to export a buffer from the Nouveau driver and pass it into the Tegra DRM driver to have it scanned out there. It looks like if you had tried to export one from Nouveau and import it back into another Nouveau instance, it would have ignored that and just calculated the parameters itself, which probably would have worked by luck a lot of the time, but I don't think it would have actually worked like you wanted it to if you specified some arbitrary layout. So I went and wired that all up so that would all work with the new modifiers only. And I added support for the new modifiers to the DRM KMS driver in Nouveau for the Tesla through Turing class of GPUs. I wired up the new modifiers to Tegra DRM, but I also left in place the support for the old modifiers so it wouldn't break the user space API. I added support for creating an EGL image from a DMA buff, and it'll take the format modifier that you pass in and initialize the proper gem buffer layout from that. And for the user space portions in Mesa here, I only bothered implementing things for the Fermi and above driver. It should be pretty easy to take that and backport it to the MV50 driver and to the Turing driver once it exists. But this is all pretty straightforward, just wiring some things up and filling out some tables and following the existing examples. And I also added support for, in addition to the existing layouts with the new format modifier, I added support for compressed buffers as well. And then the new part that I added was I exposed an extension to actually do these usage transitions in OpenGL. So this is pretty similar to the existing DMA buff format modifier queries that are out there now. There's an EGL command that lets you query a set of format modifiers that are compatible with a given source format modifier. So this will either return you an empty list or some other set of format modifiers. In the case of Nouveau, it will return you exactly one other format modifier right now that is has the opposite compression bit set, basically. So if you pass in a compressed format modifier, this will return you the uncompressed equivalent, and vice versa. So once you have that list, an application can potentially call this GL transition format modifier function. And the function signature here is basically borrowed from GL clear. So you can pass in a set of color masks that represent buffers bound to the frame buffer. And this command will take all those bound buffers and transition them from one format modifier to the new one. And so then the way an application would use this is as it's querying all its format modifiers from the different drivers it wants to use, it eventually will have to take those and intersect them to get a compatible set somewhere. And what it can do is say, well, I was going to discard this format modifier because it's not compatible with one of my usages. But before I do that, I can go and do this extra query and say, is there some list of compatible format modifiers that is equivalent to this one in some way? And if it gets some back, it can say if any of those compatible format modifiers actually fix the intersections so that it can succeed, it can keep that previously discarded format modifier in its list of potential candidates and allocate with that, knowing that it can transition to something else later if it's going to use that one in practice. So once I had that API up and designed, I had to implement it in the Nouveau backend. So let me talk a little bit here about what that means in our driver, I guess. NVIDIA 3D hardware supports, I don't remember exactly what we call it, but we have this internal lossless compression, where when we're rendering something and writing it out to our frame buffer memory, rather than send all of the actual raw bytes across the bus, we can detect that it's something that we can compress, and the rendering engine actually compresses it on the fly, and it only sends the compressed data across the bus, so it saves memory bandwidth there on the right. And then in turn, when we're reading that back to do some texturing or some other kind of operation, we don't actually read the full thing back across the bus again. We just read the compressed data back and decompress it on the fly and use that instead. So I think most 3D hardware has this these days. There's nothing NVIDIA specific about this except for our implementation. The hardware supports this for various different uses in the 3D hardware. Some support it and some don't, but the ones that don't usually can decompress on the fly and just use the decompressed data instead. And And it's supported for, I think most importantly, most common color formats and depth formats. So most importantly, it's supported for any color format that has 32 bits or more of data, I believe, on modern hardware. So we can enable this on our hardware on a per 3D engine instance basis. So if you have some 3D context, you can enable compression on that, and it'll use compression whenever it sees a compressible format. It also has to be enabled on a per mapping basis via this page kind field that I talked about earlier. So if you have a compressed page kind, and you have your page table set up right to use that compressed page kind, and you have 3D or compression enabled in your 3D engine, the hardware just automatically goes and does this compression as needed. Unfortunately, NVIDIA display hardware does not support this compression. So if you're doing the most basic thing, rendering some data to an image that you want to scan out to display to the user, you have to make sure it's not compressed data before you get to the scan out phase. Fortunately, though, we have, like I said, most of the compressed page kinds have a corresponding uncompressed page kind that use the same underlying bit layout when they're actually in memory, but just don't contain the compression metadata. So newer hardware, I think, is basically Tegra TK1 and everything that came after that, including desktop hardware, has this method where it can decompress the surface on the fly. So it takes any compressed data that's not been flushed out to memory and basically flushes it out. It behaves more or less like a cache flush. So if your compression were a cache, this would be like a cache flush operation. And as part of that operation, it also invalidates the compression backing store. So if you go back in the future and try to start doing more, if you modify the data while it's in the uncompressed format and then go back to your compressed mapping and start doing operations on it there again, it'll know that it can't read the data back from the compression anymore. It has to go and actually read it out from the memory. So we don't have to do any other additional operations to switch back from the non-compressed layout to the compressed layout again. That takes care of it automatically. Okay, so that's what I actually implemented in the prototype so far. The hardware does support some other transitions. So specifically on Tegra, we have this other type of compression that we call color decompression engine format, or CDE. So Tegra GPUs have display hardware in them that can support this other type of compression, and a couple of other engines as well that don't understand the GPU compression but can use this compression format. And so the GPUs have the capability to translate from the GPU compression format to this other compression format in place again. So this will happen without, again, sending all the bits across the bus, so you still get the memory bandwidth savings. You just have a little bit of memory bandwidth to read back and write back the compression formats. And once again, importantly, the CDE mapping is treated as read-only. So if you want to transition back from CDE to the GPU compression, it's still a no-op. The data hasn't changed, so the compression store is still valid, and there's nothing to do. So I didn't try to do this right now. I didn't have enough time to go and do this part. But it's roughly the same concept, and you would just get performance gains in more cases, basically. It'd be more broadly applicable for those GPUs that do support this. Okay, so what are the results from all this, and what are the next steps? Yeah, I didn't honestly know if performance would be better when I started this out. The compression stuff is very finicky. Sometimes it works, sometimes it doesn't. You never know. So I modified KMS Cube to use the compressed layouts and decompress in place. And if you do that, performance is roughly comparable to using not compressed, which is as expected, because you save the bandwidth when you're writing out to memory, but then you pay the bandwidth cost when you decompress. It's basically like doing a write in two parts. So you get the same performance there. If you don't decompress, you get between 50 and 300% better performance. So the compression is working. You do get very good gains when you do the rendering. But if you do this, you actually have corruption when you scan out because you're trying to read back data that's not actually there in memory. So that's not useful for this particular prototype. But again, if you had the CDE compression conversion transition implemented, then you should get something close to these numbers in practice. I wanted to have something that actually worked for the prototype that I did. So I went ahead and modified KMS Cube so that it behaved more like a composited desktop. And rather than just rendering to a buffer and then scanning that out immediately, it would render to a buffer, take that buffer and split it to another buffer, like a Wayland compositor would, and then scan that out instead. And that should have the bandwidth savings of that render and texture operation essentially being free, since they don't have to go out to memory. And so that worked out properly, and I ended up getting an 80% gain in performance versus the non-compressed and non-transition enabled case. So I was pretty happy with that. I mean, KMS Cube is kind of a toy app. It's probably the only benchmark worse than Gears. but it proves that everything's working right, and the stuff that I wired up is useful. I think in practice, if I had to estimate, if you had like a real application, you'd probably see gains of something more like 10 to 15, maybe 5% in some cases. So that is more work to do, more testing there, but I think this is enough to prove that the mechanism itself is useful and works. And so what are the next steps? Hopefully nothing this time. So once again, we need to collect feedback. I'd like to get the format modifier changes initially out and reviewed upstream. Those are pretty simple. It's just a change to drm4cc.h that defines all the format modifiers NVIDIA could want for now. So once that's upstream and agreed upon, I can clean up the Mesa patches that add the format modifiers and get those reviewed and committed. And then I'll need to write an extension spec for the transition format modifier extension. And I definitely want feedback there. I want to know if this particular API is useful for other vendors with other hardware. I've written it as an ext right now, so that hopefully other people can use it. But I need to hear feedback there. And obviously, there's the GL extension right now. We would need a Vulkan extension as well, but that's even more straightforward to write than the GL one, I think, because you can just fit it in with the existing Vulkan layout transition stuff. You just plug in format modifiers instead. Once all that's in place, you can integrate all of this with the Wayland protocols and the compositors so they can make use of it and get the same performance gains. Again, maybe not 80% in every case, but some good gains probably. And then, of course, once that's all working, we can implement the equivalent thing in our binary drivers, assuming we can work out the right interfaces to talk to the components. And along with that, there's still, as I mentioned, I'd solved the minimal theme this time, so there's a bunch of other allocator issues that should probably still be solved. Most notably, like I said, I didn't do constraints. And right before I was going to give this talk, I think Aaron Plattner pointed me to this bug on GitLab where someone said, "Oh, I'm trying to render with my AMD GPU and scan it out on my Intel GPU, and it looks all corrupt and weird. What's going on here?" And someone's like, "Oh, yeah, that's because the pitch alignment or the stride alignment isn't the same between these two cards. So one of them, they just assume different strides for the buffer, and you get corruption." If we had an allocator, it would have solved that for them. So that should probably be reintroduced into the system somewhere. And once you have constraints, you have to reintroduce capability sets. So you do need this container of constraints and how they match up to a given list of capabilities. So even if the capability is just a single format modifier, at least on our hardware, the constraints are different depending on which particular format modifier you're using currently. And then, as I said, the current design that I prototyped right now uses GBM as the allocator, and the OpenGL and Vulkan drivers and the DRM drivers as the capability constraint generators. So I don't know if that's the design we want to use going forward or not. It's just another prototype proving the mechanism out. I wanted to know, do people still want like a vendor agnostic DMA above factory that can allocate things that's vendor agnostic? It sounded like from the Vulkan WSI talk yesterday that some people still do. If you still have those use cases, send me an email or come talk to me and let me know what they are. And maybe there is still reason to have an allocator that isn't GBM. Maybe GBM can solve your use cases. I don't know. It has to be worked out. Similarly, is there a need for an API agnostic capability set generator? So something that you can submit your usage to and get back a set of format modifiers and constraints. Again, I don't know if this still is this use case. I don't know if Google's still interested in doing like a layered gralloc that goes on top of something that isn't GBM. I know various people are working already on doing gralloc on top of GBM, so maybe that's working out good enough and there's not this need anymore. The present transitions that I've implemented right now are not persistent, so you can transition to this uncompressed method and use it with some kind of other engine that uses the uncompressed mapping like our display engine. But if you went and started rendering to the same surface again in OpenGL or Vulkan, it would immediately start to compress it again, go back into the compressed format, even though you've done this transition. So to make that transition persistent across more rendering and more operations, I have to go and make sure that you can create two different mappings or modify the mapping to a surface on the fly in Nouveau to put in the different page kind into the page table entries. I don't know if there's already code pending for that in Nouveau right now or not, but I think it would be relatively straightforward to add. I think at some point NVIDIA had some code like that for the Pixel C that could do that kind of stuff, so I'll have to dig that up and see if it's still around. And there are a couple questions we had within NVIDIA as we were going through this exercise, we weren't really sure if we should have like a protected content bit in the DRM format modifier thing. Daniel's shaking his head now. This debate must have come up before, so I wasn't sure what we should do about this. It seemed like there were arguments going both ways, but we kind of left it unresolved. The protectedness is inherently like a property of the underlying memory itself. If the memory is protected, you can do protected operations on it, like scan out your HTTP data and stuff like that. So the hardware already knows whether or not you're protected. The question is just, when you're creating a mapping of that data in your hardware or somewhere else in your application stack, you have to be able to make sure that that mapping matches up with the state of the memory. So how do you pass that data around in your application stack? And there's two ways you can do that. You can pass it around, or maybe three ways even. You can pass it around by querying from the kernel, is this thing protected or not? Some people don't like that method at all. You can make it a property of you can make it a bit in the format modifier saying, I have a whole different set of format modifiers that are exactly the same except for they're protected. Or you can just pass it around as like sideband data in your application stack, whatever that be. Like Vulkan has a separate bit you can set to say this is protected memory when I'm creating an image or something. So that debate has to be had, or if it's been had, I need to be forwarded the results so I know which way to do it. And then finally, we have this really annoying thing in our hardware about how we point the mappings at the actual compression backing store. I'm not going to try to go into all the details here, and I know this has been debated a couple times before. I know that for the Intel hardware, I've seen that they have a separate plane where they pass along the compressed data as kind of a separate buffer next to their actual image data. And whenever they go and map that into Vulkan or EGL, they have to go and pass in both together. To me, that makes sense when your compression data is actually specific to that particular mapping of that buffer. But then when you get into things where you have, like in the Vulkan API, where you have multiple different mappings of the same underlying physical memory, and then you really want all those different mappings, regardless of whether or not they're coherent with each other. You really want them to share the same metadata on our hardware. Otherwise, you start to get corruption when you do things like paging memory in and out of the video memory and into system memory and stuff. If you want to know all the details, come talk to me in the hallway later on. I can tell you great stories about that. But for whatever reason, our hardware really wants the data to be tightly tied to the memory. So the only ideas I come up with for this so far are, again, to stash that in the actual DMA buff itself, which I know kernel people have pushed back pretty hard on. They don't really want any vendor-specific or usage-specific, what I would call like mapping-specific data in the core DMA buff object. But I haven't thought of another place to put it that actually works. Or we could try to do a separate plane and just require that all applications know how to use that and pass it along with every single mapping they create of the surface, even if it's not for the same usage that they're intending their compression to be used with. That seems awkward as well because the APIs that we have right now aren't designed like that. It would be a change just for NVIDIA hardware. Or I think it might be possible to append this data to the end of the buffers themselves and just allocate bigger buffers. But I'm not entirely sure that works either. I have to look into that some more. So this is another unresolved issue to work through. Questions?
So where to begin? I need to do a little bit more digesting on the whole GL modifier transition API. So right now, the way that this works on Intel is that we have compression, and compressed and uncompressed is the same modifier. It's just that we trust in the Vulkan layout transition to the swap chain layout to do that transition, and then in GL it's auto magic based off of when you export the buffer, which is admittedly not great, but it also is a very different way of doing it than what you're proposing. So I'm not sure, like, the feeling I'm getting is that what you're proposing is probably better if that's the way we had done it the first time around, but The other thing, when you were talking about storing your compression data in a second plane, we do that today, and it works
Right,
fine,
right.
and everything is plumbed to handle it.
Right, but yeah, I mean, our current, I think our upstream Tegra drivers do it the way I talked about, where we've stashed some metadata in the DMA buff by patching the kernel. Like I said, I'm pretty sure our guys have had that debate with the kernel engineers and are at an impasse, basically. I think there is something different about the way the NVIDIA hardware uses the compression data than the Intel hardware does.
Yeah, I think. Well, and we're looking at switching to a convention-based thing rather than two planes for reasons. But so we can pass it either as extra data with just a convention for here's how you calculate the offset, which works okay if you have a single sample 2D, no mip-map, no array slice surface. You can probably come up with a convention that everyone can agree on. If we ever wanted to do something more complicated, it would be a problem.
Okay.
At that point, you kind of do need the second plane. But so in terms of like plumbing things to handle the second plane, X, Wayland, all the stuff is plumbed to handle the second plane. It's just a matter of whether or not that's the convention that you want to use. And it's kind of up to your driver to decide how to do that, because it's your modifiers, you decide what to do. But the plumbing should be there in the user space components.
Right. But I realize that plumbing's there for now for like if you have, like I said, the single color mapping of the thing and you want to use that mapping consistently everywhere and have the same data behind it. What I'm worried about is the case where you have that 2D color mapping of that region of memory, but then for whatever reason it's also aliasing your depth buffer from some other usage case that doesn't run at the same time. And then you need the compression data to be the same for both those usage cases.
You allow colored alias depth buffer? That's gross.
I'll stay here. And I wanted to speak to the other part too about the. I was definitely aware that you can do the. We have paths where we can do the transition from compressed to uncompressed at the logical times too. Like you can do it as part of swap buffers. You can do it as part of the present source, whatever it's called, Vulkan transition. The problem that we always run into there is, like I said, if you just do it unconditionally there, you lose all of the perf because you flush it all out to memory, even if you're not going to ultimately put the scene into a display plane or somewhere where it doesn't have to be compressed. Is this the one that we did for the Chrome stuff? That one wasn't quite expressive enough. If I remember it. What's that? Yeah. Yeah, let's talk afterwards. I remember when we wrote that extension, I wasn't happy with it. I think it was missing something that we needed. If it works in terms of format modifiers already, then it's probably good enough. Yeah, it's the same thing.
Yeah, that's
To be fair, we're way over time. The next talk is already, we're way over time, and the next talk is supposed to start. There are a fair queue of people, including me. I didn't even bother standing up because there's already so many people. I think it might be good to move this into a workshop tomorrow. Like maybe tomorrow afternoon there's no workshop, so we could take that whole room. So I suspect, yeah, I'm in the same boat as a bunch of people, as I do need some time to digest it as well, definitely.
Yeah, and I'm happy to answer questions, on email and everything too later on. I will leave I think I have to leave around 3 tomorrow, but yeah, I'm happy to talk about it with anyone here before then as well.
Great work.
Thanks, yeah. And thanks for all the ideas. A lot of you guys inspired a lot of this. Thanks.